if we want to try to find a volume of a solid, turns out we're going to talk about a couple of methods. I guess you might say three methods. Two of them are highly related, but the first method that I want to explore is the disk method, or sometimes you'll hear it called slicing method. But it's based upon the volume of a disk, doing disk. Area we started by approximating with rectangles. Well, sort of, we're not going to really do any approximating, but for volumes, this first method we start with using disks. And let me explain what I mean to you by a disk. A disk, well, it's kind of a cylinder turned on its side, kind of maybe narrower. I don't know if you can see that, but yeah, just think of a penny or something turned over on its side, or straight up and down like that. It's really just, it's a cylinder turned like this. Now in a cylinder, we're usually, here's, I don't know if you can see my visualize with my drawings or not, but that's what I'm talking about, a cylinder, which the volume is pi r squared times h, where the radius is of the circle, and then the height is the height of the cylinder. Well, that's what I'm saying. A disk is just a cylinder turned over on its side, and so the volume is pi r squared. It's just kind of the orientation of the thing is a little different because the radius is over here, and then the height is really not a height, it's kind of more of a width. And that's a good way to think of it because that's the way we'll have to deal with it mainly there. But the radius is the radius of the circle, height is the width. But that's what we refer to when we're talking about disk method. Okay. All right. So how does that get involved in volumes of things? Well, here's how it goes. Let's say that I take a function like so. Y equals f of x. So that's just a two-dimensional, that doesn't have any volume to it. How do we get volume to it? Well, the way I get volume to it is I take this function from A to B here. I'm going to make it a little bit closer to the x-axis here. At B. I take that area, if you will, from A to B, and I rotate it about the x-axis, 360 degrees. And it comes out, goes back into the board, if you will, and then spins back around. And so we get this, I want to call it kind of a vase shape. If I do that 360 degrees around, so I get this vase, I will try to draw it. But it's probably a little wider there at the mouth, but it's a solid. Kind of a bob, what are those things? Squeeze balls or something. Just kind of get you a visual, but my drawings aren't always going to be the best, but I want to find the volume of that thing. It turns out with a little bit of calculus we can do that. Now how do I do this? Well, I use the rectangles, but then I rotate the rectangles and get discs. That's how this is going to work. So I'm going to take let's see, I did 4. Divvy this up from A to B. Into 4 rectangles. 4 rectangles. And I'm going to use right-hand endpoints. You can use midpoints. Whatever. Okay? We're used to that. All right? And then I rotate those. Rotate each one of those about the x-axis. Well, that's where I get those discs, because when I rotate those about the x-axis, those give me the disc, right? Because if I rotate this rectangle all the way around and then back through the board, back around, that's going to give me a disc. And same thing for all these. Let me draw the smaller one here first. So the smaller one will be a disc kind of like this. And then this one will be a little bit bigger disc. Helps to have a drawing to look at to help me draw it anyway. So it's a little bit bigger. But it also gives me a disc. That's our biggest disc, so it's probably bigger than this one. Something like this. And then this is a little bit smaller, so it just kind of peeks out there. You just want to draw it, right? 4 discs. Well, guess what? These discs approximate this volume, doesn't it? The volume of these discs is approximately the volume of this vase shape. Right? You see that? Sort of? I mean, if you do more discs, more rectangles, it matches it better, of course, as with any case. But you see the idea? So the volume of these approximates V. This volume here. With me? So let's think about the volume of each disc. Well, good thing about the disc, we just talked about that, the disc is pi r squared h. Right? Or to put it another way, it'd be pi, since it's a disc, times the radius squared times the width. So it's, let's just look at one in particular here. So I need that radius, and then I need that's our h, but that's more of our, we call it width. Well, let's start kind of with the easiest one first, I guess. Remember here, these subintervals, we call it x1, x2, x3, and this will be x4, and this will be x0. Right? And so the radius here, this would be the radius, but what does that match? Well, it's that. Wouldn't that be the radius? Following the pictures here? That'd be the radius. How do I get that radius? Well, it's whatever that function value is at x4. This radius is here. It's that function value at x3. You with me? This would be the function value at x2. This would be the function value at x1. Or if I use midpoints, it's the midpoint at each of those x sub i's. So the radius is going to be the function value of whatever x sub I I'm talking about, squared. Good with that? Because I square the radius. That's the volume of a cylinder disc. Now what about the width? Well, the width of these things, isn't the width, this is the far one, this is the width. Aren't those widths all the same? What are the widths? Aren't they each delta x? The difference between each of these x sub i's is delta x. So the widths are delta x. So each disk is pi times the function squared, function at x sub I squared. Since I use right-hand endpoints, if it was midpoints, it'd be the x sub I bar. If I use left-hand endpoints, it would be, whatever. Well, each one of those, so what's the volume of this whole thing? So the volume of all the disks would be every one of those. I would just add up this one plus this one plus this one plus this one. Well, the easy way to do that is say, well, it's the sum. I equals, I've got 4 here, so it'd be I equals 1 to 4. Add up all of those, plug in the x sub I to your function. See where that comes from? How do I get it better though? Because this is just an approximation of this volume, right? How would I make it better? Make more disks, right? Make it 10 disks or 100 disks. How do I get it exactly though? That's really the question. Well, I would do I equals 1 to n pi times f of x sub I squared times delta x. But to get it exact, that's just going to give me an approximation. To get it exact, I would do infinitely many. So I'd run the limit of n to infinity. What does that remind you of? The limit of n goes to infinity of this Riemann sum stuff. It's an integral, isn't it? This is an integral. So the volume is, this is kind of the definition of integral. Pi times f of x squared, delta x is dx, and then I'm going from a to b. That's the disk method right there. Called disk method because it's generated by using disk. And to get a little more specific, it's rotating y equals f of x, volume of solid found by rotating y equals f of x about the x-axis. Because as you can guess, we are going to rotate some about the y-axis, but this is the one rotated about the x-axis. From x equals a to x equals b. To be more specific about it. This is called the disk method. So that's a formula you might want to hang on to right there. All right? So let's do one. All right, so let's find the region bounded by y equals square root of x equals 4, y equals 0. That is rotated about the x-axis. Find the, whoops. Gotta say the volume. Find the volume of the region bounded by y equals square root of x equals 4 and y equals 0, that is rotated about the x-axis. Statement of these is a little wordy, but okay. And use the disk method. We'll make a point or two here about it as we go along. But all right, so let's draw it in. Y equals square root of x looks like this. X equals 4, well, that would be here, so that would be this. Y equals 0, that's the x-axis. So I'm rotating the region bounded by all that about the x-axis. And sometimes it's fun to draw, think about what shape you get here. Well, the shape here I would get, wouldn't it kind of be kind of a bullet shape? So I'm finding the volume of this shape here, sort of, my rendition of it. Yeah, this is the disk method. So the disk method says do volume equals integral from a to b pi times f of x squared dx. Well, integrate with respect to x, so I want to go from 0 to 4 in the x. Pi, so what's my f of x? Well, it's y equals square root of x. So when I take pi times that squared, square root of x squared dx. And so that's, that's a little tricky. We're not just doing the function, we're doing the function squared. Which in this case is going to work out pretty nicely because of our function, but that'll find the volume of that thing. So, like I said, this one's going to work out pretty nicely because that's square root of x squared, that's just x, isn't it? Square root and square cancel. And it's just pi, a number, times x, so it'd be pi. The antiderivative would be pi times the antiderivative would be 1/2 x squared. And then go from 0 to 4. So that would be pi times, be 1/2 times 4 squared, be 1/2 times 16. Minus plugging the 0, be 1/2 times 0 squared. It's 8 pi. That's 8, that's 0. 8 minus 0, it's 8 pi. Yes? That's fine with that then. Whatever shape it looks, it is. The volume of it is 8 pi units cubed. Now, one thing I did mention on the formula there, but that will be important because of later on, it won't tell us which method or which way to integrate this, but the typical rectangles again, let's notice something about this. So I'm integrating with respect to x, so we already kind of knew that. But notice this. A typical rectangle is vertical, that's we integrate with respect to x, so it was kind of given. But, like I said, this could be coming in handy here to note this. Do you notice here the typical rectangle and the axis of rotation, the x-axis, how those are related? They're perpendicular. In the disk method, that's the way it works. Your typical rectangle is perpendicular to your axis of rotation. So we might want to make that a little note. If typical rectangle is perpendicular to axis of rotation, that is disk method. Or slicing method. All right. May not seem that important right now because that's all we've got is disk method, but we'll get another method or two here. And that little note will definitely come in handy down the road. All right, just a couple of others here. All right, so let's find the volume generated by rotating the region bounded by, so these questions are a little wordy, the statement of the problems. Find the volume generated by rotating the region bounded by y minus 2x equals 1, comma, x equals 1, and x equals 5. About the line y equals 0. All right. We've encountered different versions of lines. However you want to graph to get the graph, however you want to. That one, I can see us using the intercepts. Y equals 1 is the intercept. Y-intercept negative a half is the x-intercept. So graphing it, that would be one way. X equals 1, be the vertical line. X equals 5, that vertical line. So I'm taking that region bounded by those. That's what I mean anyway. Probably should have thrown in y equals 0, but find that rotate that about the line y equals 0. So I wanted to so the line y equals 0, that's just another way of saying the x-axis. So don't let that fool you. So I'm still doing pretty much what I was doing here, rotating it about the x-axis. I should have thrown in y equals 0 here. Anyway, yeah, so again, kind of fun to draw, think about. So this would kind of be something like this, if I did that. It's kind of a cut-off cone. They call it frustrum of a cone sometimes. This is circular there, but yeah, you kind of get that tapered, almost a lampshade tube. You don't have to necessarily draw that. Just fun to think about what these shapes are. I want to find the volume of that. Well, again, using this method. So A to B, obviously it's 1 to 5. Pi times f of x squared, well, the f of x here, all right, so yeah, that, what is f of x here? Well, they didn't quite give me f of x because they gave me y minus 2x, so to get the f of x, add the 2x, right, to both sides? So y equals 2x plus 1, that's my f of x, so I would square that. So it would be 1 to 5 pi times 2x plus 1 squared dx. Now, there are a couple ways to do that. Probably most of us, since it's just squared there, we probably go ahead and square that out. 2x plus 1 times 2x plus 1. So it'd be 4x squared plus 2x plus another 2x would be 4x plus 1. If it's squared, that's not too bad. You just multiply that out. Then I can just do my antiderivative, that'd be 4/3 x cubed, 4/2 x squared, plus 1x, then do that from 1 to 5. And usually what we do is just evaluate this and then multiply the pi in. It'd be 4/3, 5 cubed is 125. That'd just be 2 times 5 squared, 2 times 25, plus 5, and then subtract by plugging in the 1, that'd be 4/3 plus 2 plus 1. Whatever that gives me. I get 652 over 3 for all that. So it's 652, probably how you see this. 652 thirds times pi. Be the volume. Okay.